Welcome back to our podcast, where we explore the fascinating world of technology and data processing. Today, we're diving into an intriguing topic, the transition from batch processing to stream processing. If you've ever been curious about how data flows in real-time systems or how events are managed in a streaming context, you're in the right spot. So grab your headphones and let's jump in. In batch processing, inputs and outputs are usually files that sit on distributed file systems. Now, how does this compare to streaming? In the realm of streaming, the equivalent of a file is a continuous flow of data, often referred to as events. An event is a small, self-contained, and immutable object that captures the details of something that happened at a specific moment in time. Each event typically comes with a timestamp, marking when it occurred. Events can come from a variety of sources. For instance, they might arise from user actions, like viewing a web page or making a purchase. Alternatively, they can originate from machines, such as periodic readings from a temperature sensor or metrics on CPU utilization. Think about a web server log. Each line in that log is an event. When we process these events, the first step involves parsing them into a sequence of records. This parsing enables us to store events in different ways, whether that's appending them to a file, inserting them into a relational database, or sending them over a network to another node for processing. In batch processing, a file is typically written once and can be read by multiple jobs. In contrast, streaming systems group events into topics or streams. A producer generates events and writes them to a data store, while consumers read those events, often polling the data store for new entries. This is somewhat similar to how batch processes operate when they handle a day's worth of data at the end of each day. However, polling can be inefficient. The more frequently a consumer polls, the less likely they are to retrieve new events, leading to increased overhead. Instead, it's often more effective for consumers to be notified when new events are available. While relational databases do have triggers that react to changes, their functionality is limited. This limitation has spurred the development of specialized tools designed for delivering event notifications. Let's delve into how events are transmitted in a streaming context. In a typical messaging system, a producer sends a message containing an event, which is then pushed to consumers. This setup is more complex than a simple Unix pipe or TCP connection that connects one sender to one recipient. Messaging systems allow multiple producers to send messages to the same topic and multiple consumers to receive those messages. When considering how these systems manage message flow, we can ask two critical questions. First, what happens if producers send messages faster than consumers can process them? There are generally three approaches: dropping messages, buffering them in a queue, or applying back pressure, which blocks the producer from sending more messages until the consumer can catch up. The second question revolves around what happens if nodes crash or go offline. Are any messages lost? Achieving durability often requires a combination of writing to disk and replication, which can incur costs. Depending on the application, some message loss may be acceptable. For example, with periodic sensor readings, losing an occasional data point might not be critical. However, in scenarios where accurate event counting is essential, any lost messages can lead to significant errors. Many messaging systems offer strong reliability guarantees. For instance, if a task fails, it can automatically retry, ensuring that the output remains consistent as if no failures occurred. This reliability simplifies the programming model, which is crucial in stream processing. There are various ways to implement messaging systems. Some rely on direct network communication between producers and consumers, while others utilize message brokers. Brokerless messaging libraries like ZeroMQ and NanoMesk enable publish-subscribe messaging over TCP or IP multicast. On the other hand, message brokers function like a database optimized for handling message streams. producers send messages to the broker, and consumers retrieve them as clients. The advantage of a message broker is that it manages connectivity issues, allowing producers and consumers to connect and disconnect without losing messages. Some brokers keep messages in memory, while others can write them to disk for durability. When consumers are slow, brokers can allow unbounded queuing, although this might impact performance. When a producer sends a message, it typically waits for the broker to confirm that the message has been buffered rather than waiting for the consumer to process it. This asynchronous delivery means that consumers may receive messages at an undetermined future point in time, which can vary based on the system's load. A key distinction between message brokers and traditional databases is that brokers usually delete messages once they have been successfully delivered. This makes them unsuitable for long-term data storage. Additionally, while databases support complex queries and snapshots of data, message brokers notify clients when new messages are available, which operates under a different mechanism altogether. Common messaging protocols like JMS and AMQP are implemented in software solutions such as RabbitMQ, ActiveMQ, and Google Cloud PubSub. These systems can facilitate various processing patterns, balancing workloads among multiple consumers, or enabling fan-out delivery, where each message is sent to multiple consumers. In a fan-out scenario, each consumer can independently process messages without affecting others, much like having multiple batch jobs reading from the same input file. This flexibility is crucial for scaling applications and managing high-throughput scenarios. However, with acknowledgement systems, if a consumer fails to acknowledge receipt of a message, the broker assumes it wasn't processed and will attempt to deliver it again. This can lead to complexities, especially if the acknowledgement itself is lost in transmission. Handling such cases often requires robust protocols to ensure data integrity. As we wrap up today's discussion, it's clear that the shift from batch processing to stream processing introduces a host of new concepts and challenges. From understanding how events are generated and processed to exploring the intricacies of messaging systems, we've only scratched the surface of this vast topic. Whether you're a developer, a data engineer, or simply a tech enthusiast, grasping these principles is essential for navigating the evolving landscape of data processing. We hope you found this episode insightful and that it sparks your curiosity to learn more about stream processing and its applications. Thanks for tuning in, and we'll catch you in the next episode.